So today we're going to investigate and look at mathematical induction, which is a type of proof. It's not like a geometry proof, it's a little bit different than that. But before we start, let's review some algebra skills that are always needed when you do a proof by induction. So the algebra that we always need to do is finding the k plus first item. So let's look at some examples. So example A says that P sub k is S sub k equals k squared k plus 1 over 4. So if I want to find the statement for P sub k plus 1, that means that all of my k's need to become k plus 1. So and really the only simplification that I can do is this right here, this piece. So we're going to clean that up. K plus 1 is k plus 2. So we can write our final answer as k plus 1 squared times k plus 2 . Oh, sorry, you know what? I forgot the square on this one, which means this one has a square on it, which means this one has a square on it, all over 4. So all we're doing in this set of examples is replacing k with k plus 1 and doing the algebra. Let's do another one. Make that a lot smaller, put it up there. Let's do letter B. Letter B says that P sub k is S sub k equals 1 plus 5 plus 9 plus ... plus brackets 4 k minus 1 minus 3, close your bracket, plus 4k minus 3. So all I'm going to do is I'm going to replace all my k's with k plus 1s. So P sub k plus 1 is S sub k plus 1 equals 1 plus 5 plus 9 plus ... plus 4 k plus 1. And then I still have right here this minus 1 minus 3 plus 4 k plus 1 minus 3. So in here, this piece right here is really just a k, because plus 1 minus 1 makes just a k. So then I have 4 times k, and then minus 3. This one, I get 4k plus 4 minus 3, because you have to distribute the 4 in. So this is really 4k plus 1. So now let's just clean it all up and write it nicely. One last time. 1 plus 5 plus 9 plus ... plus bracket. We talked about this one was really just 4k minus 3. You really don't need the brackets. You can just put parentheses if you wanted. Plus parentheses 4k plus 1, like that. Okay, let's do some more examples. Okay, so example C. C says that P sub k is S sub k equals k plus 3 less than 5k squared. So if I want to find the statement for P plus k plus 1, P sub k plus 1 is going to be S sub k plus 1 equals k plus 1 plus 3 is less than 5 times k plus 1 squared. This side I can clean up into k plus 4 is less than 5 times k plus 1 squared. That's your answer. Okay, last one of these practice before we jump into some induction. Letter D. Letter D, I think your notes might have had a typo, so we're going to fix it. P sub k is S sub k equals 3 to the k. Here's the typo, greater than or equal to. It should not say what it says. If it says 5k squared, that's not right. It's supposed to say 2k plus 1. This piece right here, make sure that's what it says right there. Okay, so if I want to find P sub k plus 1, S sub k plus 1 is going to equal 3 to the k plus 1 is greater than or equal to 2 times k plus 1 plus 1. A little bit of algebra. This is 2k plus 2 plus 1 more, so this is really 2k plus 3. So if we were to write our answer nicely, it'd be 3k plus 1 is greater than or equal to 2k plus 3. So that's the algebra steps that you need. And so now we're going to jump into doing the mathematical proof. So this is the steps that we're going to take. We're going to make some statement for P sub n. We're going to prove it true for P sub 1. And then we're going to pretty much make the n become a k and assume it's true and then prove it for the next term. So here's kind of what happens. I have some statement, P sub n. It's just some statement. It's some thought, some algebraic, whatever. So step 1, if this is going to be true for anything, I must at least be true for the first thing. So I prove that I'm true for the first thing. And you're like, great, I did that. So now we go down here and we say, okay, instead of calling it P sub n, what if I change the n to a k? I mean, they're all just letters and variables, so it's not a big deal either way. So I assume if it's true for P sub 1 that I'm true for P sub k, and then I need to prove that I'm true for P sub k plus 1. Because here's what happens. If you can prove that I'm true for P sub k plus 1, what you're really proving is that you're always true for the next thing. And if you're always true for the next thing, then you're true for all things. It's like that game of, well, tell me a number, or the biggest number you know, and someone will say 100. Okay, well, I'm going to say 101. And they'll be like, okay, 1,000. Okay, 1,001. I always go one bigger. I'm always proving it for the next thing. And if I always prove it for the next thing, then that's proven, then you prove it for the next thing, and so on. So let's kind of jump into the process. So the first one that we are given to prove is that S sub n equals 1 plus 3 plus 5 plus 7 plus 2n minus 1 equals n squared. And then it says for all integers n is greater than or equal to 1. Okay, so the first thing we have to do, first step, is you have to prove S sub 1. S sub 1 really just means I'm taking just the first term. So you can say S sub 1. In this case, my first term right here is 1. The other thing you could do, is you don't believe that, S sub 1 equals, take this piece, the formula they give you, 2 times 1 minus 1 is 1. And then you use what they tell you it equals, and you're asking, does this equal n squared, which in our case is 1 squared? That equals 1. So right here, this 1 equals 1. Great. We proved it for S sub 1. So now, after we prove it for S sub 1, we move on to the second part of the proof. So step 2 has 2 parts. Part A is you assume this statement's going to hold true for S sub k. Just because I have S sub n, why can't I call that n's k's instead? So then we say we're going to assume S sub k equals 1 plus 3 plus 5 plus 7 plus ... plus 2k minus 1. And this is going to equal k plus 1. No, not k plus 1, sorry. This is going to equal k squared. All I did is this formula right here where I'm drawing a blue dot. I replaced all the n's with k's. So here is my assumption. Now this assumption is very important because you're going to use it in the next step. So my next step, B, is you're going to prove that it's true for S sub k plus 1. So let's go ahead and do that. So first of all, let's write out what S sub k plus 1. S sub k plus 1 equals 1 plus 3 plus 7 plus ... plus 2k minus 1 plus, I have to add one more term on because this up here, this was a k, this was my kth term. But now I'm doing k plus 1, so I have to add on the k plus 1 term. So for that, it's going to be what this formula was before it. Oops, that's not what I wanted. Hang on. Oh, no. Okay, so that's going to be parenthesis 2 times k plus 1 and then minus 1. This is going to now equal not k squared, but k plus 1 squared. So first things first, I'm going to clean this thing up right here. This becomes a 2k plus 2 minus 1, which is really 2k plus 1. Okay, now here's the piece that always happens. So when you write this whole thing out, look at this magical green box. This magical green box is the same thing that I wrote right here. And we know that that thing that I just boxed in green is equal to this. So this big green box right here, I can replace it with a k squared plus, oops, plus my 2k plus 1, that's this thing right here, that I cleaned up. Okay. The thing you're always trying to prove is this. Like, we're trying to get to this to prove that what we're saying is true. So if this is going to hold true, then my ending result needs to look like this. So what we're going to do is then I'm going to take what I have right here. And if you look in my gray bubble, that thing is factored. So let's factor this. Well, k squared plus 2k plus 1 factors. In fact, it factors into k plus 1 times k plus 1. Well, by golly, that is the same thing as k plus 1 squared. And now you have proven that this formula that we had holds up for the k or the k plus 1 sum or term. And so since it always holds up for the next term, then it holds up for all terms, and you've proven it by induction. So let's try the next one. The next one says that I have S sub n equals 1 squared plus 2 squared plus 3 squared plus 4 squared plus ... plus n squared. This is going to equal n plus 1, 2n plus 1, all over 6. And it says for all integers n is greater than or equal to 1. And that's pretty much always true in induction. N is greater than or equal to 1 because they're using n as the counting numbers. Counting numbers are the things you learn to count with. 1, 2, 3, 4, 5, 6. Not 0. So 1 and the integers that are larger. So now, step by step, here we go. So piece 1 is that we have to show it's true for S sub 1. So S sub 1 is going to equal, take this right here, that formula, plug in a 1 squared. 1 squared equals 1. Now you're asking, does that equal my formula? So my formula says all the n's need to become a 1. And this is going to equal 1 times 2 times 3 all over 6, which is 6 divided by 6. And look, by golly, the 1 equals 1. We proved it. So there's the first step. Part 2 is A. We assume this is going to hold true if we just magically change the n to a k. I mean, what's the magic in calling an n? It could be called k. It doesn't matter what it's called. So then we can assume it's true for k. So 1 squared plus 2 squared plus 3 squared plus 4 squared plus ... plus n squared has to equal n plus 1, 2n plus 1 all over 6. And then B is we have to prove it for s sub k plus 1. So this should be 1 squared plus 2 squared plus 3 squared plus 4 squared plus ... plus n squared. Oops, not an n though. I changed. Oh, I made a mistake over here, guys. I'm so sorry. Let me fix this. These shouldn't be n's. These should all be k's because I changed all the n's to k's. So plus k squared equals k plus 1. 2k plus 1 all over 6. So down here, going to be a k squared. Now remember, I don't just go to k, I go to k plus 1. So this should be plus k plus 1 squared equals k plus 1. This is going to be k plus 1 plus 1. And then 2k plus 1 plus 1 all over 6. I'm going to rewrite this formula one time. This is k plus 1 times k plus 2. And then this piece right here, 2k plus 2 plus 1 is 2k plus 3 all over 6. So that's what I'm looking to prove. So grab my highlighter. So this whole piece right here in my green box is the same thing we wrote up here. And we know that thing right here that I'm coloring in green, this green box, is equal to this right here. So I'm going to take this and plug it in right there. So when you do that, you're going to get, okay, so this thing equals k. So it's going to equal k times k plus 1 times 2k plus 1 all over 6. Now be very careful. Very careful right here. I'll choose yellow. I still have to add this guy down here. Plus k plus 1 squared. First things first, if I want to add these fractions, I'm going to turn my second piece into a fraction by multiplying by 6 over 6, which is the same thing as multiplying by 1, so no big deal. So when I do that, I now get k plus 1, 2k plus 1, plus 6. I'm going to write something a little bit differently for a certain purpose, so just hang on with me. K plus 1 means k plus 1 squared means k plus 1 times k plus 1. And this whole thing is over 6. Now if we're looking, this thing is Gucci. It's great because it matches the formula I'm trying to get to. What I'm going to do is I'm going to factor. This first piece has a k plus 1. The second piece has 2k plus 1s, but I'm only going to pull one of them out. So I'm going to factor out a k plus 1 out of both pieces. So this is going to equal, I'm going to pull out the k plus 1. I'm going to put a bracket. That leaves me with a k times a 2k plus 1 plus a 6 times a k plus 1. And this whole thing is over 6. So if we go back to talking about what's good and what's not good, now look, I not only have my 6, but I have this k plus 1 right here, which is this k plus 1 right here. So I need the thing that is, or the stuff right here that's in the brackets. I need this stuff hopefully to clean up into what I have up here that I haven't highlighted yet. So let's see if that happens. Hopefully it does. Oops. So let's see. This equals k plus 1, which we know is good, over my 6, which is good. In these brackets, if I distribute the k in, I get 2k squared plus k, plus distribute the 6 in, 6k plus 1. So I'm going to grab a different color. We'll do black for a second. I'm just going to pick this piece up. I'm going to pull it over here to the side. Let's do some math. This is really 2k squared plus 7k plus 1. Nope, not plus 1. I messed up. This is a 6. I didn't distribute to both. This is a 6. I'm going to factor. And the only reason I'm saying factor is these two pieces right here are factored. So I'm hoping that when I factor this thing in black, that I get to the two things I'm missing. So a times c is 12. 2 factors of 12 that make 7 are 4 and 3. So I can write 2k squared plus 4k plus 3k plus 6. I haven't changed anything. I've just rewritten the 7k as a 4 and a 3. Make your groups. There's a group. There's a group. My first group has a 2k in common, and they're left with k plus 2. Second group has a 3 in common. You're left with a k plus 2. This has a k plus 2, and so does this, so you can factor out a k plus 2. And then you get a 2k plus 3. Oh, look, this is what I was missing up here. Look. So you proved it, guys. Here we go. K plus 1. We know this big blue bracket thing factors into and cleans up into k plus 2 and 2k plus 3. And this whole thing is divided by 6. And this thing that I'm boxing is what we had right there. So we proved it. Great job. Let's try another one. So the next one says that I want to prove, I want to prove that, this is number 4. I need to prove that n is less than 2 to the n, and it says for all positive integers n. So n is greater than or equal to 1. And n is an integer. Okay, so here's our steps. So step 1, we need to show that it's true for s sub 1 or p sub 1. So if I want to do that, 1 is less than 2 to the first. 1 is less than 2 to the first is just 2. 1 is less than 2. Great, it's true. So then 2a. We assume this must be true if I may call it k, s sub k. So that means that k is less than 2 to the k. We assume this. Part B is then we do s sub k plus 1. Now that's going to say k plus 1 is less than 2 to the k plus 1. And this is what we're looking to prove. Okay, let's take a little thought real quick. Two to the k plus 1 is the same thing as saying 2 to the k times 2 to the first. Because if we have the same bases, then we add the powers together. So I'm going to use that thought. K plus 1 is less than 2 to the first, or 2 times 2 to the k. Now this step here is always to use this assumption that you made. So if I'm going to use that assumption that I made, let me just see if I can make you follow this thought process. I know from my assumption, I'm going to use my assumption right here. I know that 2 to the k is greater than k. It's the same thing I have written in my red box. But my problem is right here, I don't have just a 2 to the k, I have also a 2. So what I'm going to do is I'm going to multiply both sides here by a 2. And so now I have 2 times 2 to the k, which is what I had right here, is greater than 2k is the same thing as k plus k. And k plus k, we know, is greater than, and that thing is bigger than k plus 1. So now we can go back and rewrite this. This right here is 2 to the k plus 1. That's bigger than 2k, which is bigger than k plus 1. And what I really don't need is this middle term. If this is bigger than this, and this is bigger than this, then the 2 I need is this and this. So what I can now say is that I proved is that 2 to the k plus 1 is greater than k plus 1, which is what I was trying to prove right there, and I did it. Okay, let's try another one. So my next one says I need to prove that 3 is a factor of 4 to the n minus 1 for all positive n. Okay, so let's do this. Step 1 is you let n equal 1, and then you have to show that it's true. So 4 to the n minus, this is a minus tall 1, minus 1, I'm going to plug my n in, so I get 4 to the first minus 1, which we know is 3, and 3 is a factor of 3. So we're good with with n equals 1 or k equals 1. So then 2, part A, we assume this has to be true for k, which would give us that 3 is a factor of 4k minus 1. Part B is that we need to then prove 3 is a factor of, and this is where we do the 4k plus 1 minus 1. Okay, so here we go with the math. 4 to the k plus 1 minus 1. Let's see, what can I do with this? Well, I'm going to do something a little bit tricky and outside the box, but it really helps out. I'm going to rewrite this as 4 to the k plus 1 minus 1. And in the middle here, I'm going to minus 4k, and I'm going to add 4k. And if you add those two things together, you get 0. You get absolutely nothing. So I haven't changed anything. But the reason I did that is I can now go in here and try to do a little bit of factoring. Let me rewrite this. This right here, again, remember, this is 4 to the k times a 4. In the first group, this one right here, they both have a 4 to the k. So I'm going to pull out a 4 to the k, and you're left with 4 minus 1 is your placeholder. Plus, the next one doesn't factor, so I just get 4 to the k minus 1. So let's look at what we have. This right here is really a 3. So I can write this as 3 times 4 to the k. And this piece right here, we know from our assumption that 3 is a factor of it. So I can do plus 3 times 4 to the k minus 1. I can pull a 3 out of it because we know a 3 will go into it evenly. And then I'm going to divide by 3 just to make it even and not change anything. These both have a 3 in them. And so I can write one last statement. Oops, sorry, I was trying to move that. I can write one last statement. If I pull out the 3, I'm left with 4 to the k plus 4 to the k minus 1 divided by 3. But since I have a 3 out front, 3 times anything will always allow that anything to have a factor of a 3. And so this statement right here proves it. Since 3 is a multiple of this statement, 3 is a factor of 4 to the k plus 1 minus 1. So you've proven it. A little bit of finessing it to make it happen, but it's definitely been proven. So I'm being very honest with you, induction is not something that I use personally a lot, but I did recently use a lot more of it. And the more that you do it, the easier it becomes because you learn the algebraic tricks to massage out the issues you're having to get to where you need to be. So practice makes perfect. I know it's probably not what you want to hear, but it's the truth. Okay, so let's do some a little bit easier problems. So these formulas are given in your notes, and I'll be very honest, I would never expect you to memorize them. I'm only going to use them, maybe prove them, but I would never expect you to memorize them. So our examples say, letter A says, I need to find the sum of I equals 1 to 7 of I cubed. And since this is an I cubed, I'm going to go to the formula that has the n cubed in it. Okay, so I'm just going to use this formula, the sums of powers of integers. So if you have a single term cubed, the sum comes out to be n squared times n plus 1 squared all over 4. The n is the ending term right here, the 7. So all we're doing is if I want to find the sum, instead of listing every term out and adding it up, I just plug in the 7. So 7 squared times 7 plus 1 squared over 4. 49 times 64 over 4. 64 and 4 reduced to 16 over 1. And then the sum comes out to be, 784. Let's try another one. Letter B, a little bit trickier. It says I want a sum from I equals 1 to 6 of 6i minus 4i squared. Oh, one more mistake. Doesn't go to the 6th. This one only goes to the 4th. Okay, so we can use some properties of sigma notation to break this apart. So first thing I can do is I can write this as the sum of I equals 1 to 4 of 6i minus the sum as I equals 1 to 4 of 4i squared. Can break it into two sums. I can also push that coefficient in the front. So 6 times I equals 1 to 4 minus 4 I equals 1 to 4 of I squared. Oops, forgot the I right there. So then this I, that I right there is this n right here. So what I'm going to do is I'm going to replace it with its formula n times n plus 1 over 2. Don't forget your 6 in the front. Minus the 4 in the front, 4. And this I squared is my n squared. So n plus 1, 2n plus 1, all over 6. So my n is this 4 up here, the top index. So all of my n's need to become 4s. So I have 6 times 4 times 5 over 2 minus 4 times 5 times 2 times 4 is 8, plus 1 more is 9, all over 6. Okay, so this is going to be 20 over 2, which is 10. So I have 6 times 10 minus 4. Let's see what I can reduce to. This reduces down to, I can take a 3 out. So a 2 and a 3. So this is a 20 times a 2, which is a 60 over 2. Okay, well, I can reduce again. This is a 2 and a 1. So this equals 60 minus 120, which results in an answer of a negative 60. So these are just using some sums of powers of integers. So what I'm doing is I'm doing integers n to some power, and then I'm summing them all up. That's what that means, summing them up. So it'd be like if n was 1. 1 to the a plus 2 to the a plus 3 to the a, whatever that power is. This one, the power is 1, power is 2, power is 3, power is 4, power is 5. Okay, last problem. I skipped one in this pattern recognition. I skipped forwards. We're going to go backwards now. And it says, find the formula for the infinite sum and prove its validity. So here we go. 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over 4 times 5 plus ... plus 1 over n times n plus 1. So first things first, it says I have to find a formula. So let me find the formula first. So let's find it first. So my sum, if my term is 1, it's just 1 over 1 times 2, which is 1/2. My sum, if my index is 2, is I have to take my first term, the 1 over 1 times 2, plus the 1 over 2 times 3. Well, the first term we know is 1/2, plus a 1/6. And you can change your half into 3/6. So this is going to equal 4/6, which we know is 2/3. I'm going to highlight really quick so I don't lose these. So here's my first term, or my first sum. Here's my second sum. Let's find my third sum. So S sub 3 is going to be my first two, these two right here, which we know is 2/3, plus my next one, which is 1 over 3 times 4. Well, that's 2/3 plus 1/12. I can change this into 12ths and make it 8/12. So this is now 9/12, which we know is 3/4. And this keeps going. But let's talk about this. This is I'm looking for my pattern right now. So what appears to be happening, it's my guess, is the top is always 1 bigger than the bottom. 1 over 2, 2 over 3, 3 over 4. So to make sure that I'm always 1 bigger than the bottom, if I call the top n, then my bottom has to always be n plus 1. So my formula, find the formula. So here's the formula that I hypothesized represents the sequence. The series is the adding piece, but there's my formula that I hypothesized. So it says then I have to prove its validity. So now I have to prove that formula. So let's prove that formula. So in step 1, I have to show that it's true for S sub 1. So S sub 1 would equal 1 over 1 plus 1, which equals 1 over 2, which is what we have right here. So that worked. Great. In step 2a, we assume this is going to be true for S sub k. So this should equal 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over 4 times 5 plus plus 1 over k times k plus 1. So we assume that to be true, and then I have to prove it for the k plus 1 term. So this thing should be 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over 4 times 5 plus plus 1 over, be careful, k times k plus 1 plus, oh, sorry, I forgot. We need to plug our formula in right here. We are assuming that this would be k over k plus 1. Plus, I have to add in my k plus first term. So this should be 1 over k plus 1. And then when I add a 1 here, k plus 2. And this should equal k plus 1 over k plus 2. So reminder, this red box is what I'm going to try to show. Show or prove that. I need to get to that. So here we go. Remember, go back and use your assumption step. So this whole thing right here, by assumption, equals this. And this piece right here, up until that last term, is the same. So I can call this piece right here k over k plus 1. And then I have to add in my last piece over 1, or plus 1 over k plus 1 times k plus 2. So now what I need to do is do some algebra. I need to get to that magic red box. So let's make that happen. So if I want to add these two fractions, I need to multiply this one by k plus 2 over k plus 2. So you're going to get k plus 2 times a k plus 1 over k plus 1 times k plus 2. Up top, you're going to get a k squared plus a 2k plus a 1 over k plus 1 times k plus 2. I'm going to factor that top. That top factors into k plus 1 times k plus 1 over over k plus 1 times k plus 2. And magical math, k plus 1 and k plus 1 cancel out. So you're left with k plus 1 over k plus 2, which is what I was trying to prove in my red box. I did it. So if I were to summarize this as simply as I can for you. So step 1 is you show it's true for p sub 1. Step 2a is assume true for p sub k. Because up here we start with some p sub n. So what does it matter if I change the end of the k? They're just letters. It shouldn't matter. It should still hold true. And then b is that we prove p sub k plus 1, the next term. And the trick in using this is two things. Use the assumption in 2a and use your algebra skills. The more you practice, the easier it is. There is one of these on the test, and you have my word that the algebra involved is not overly intensive.